In this lesson, we're going to take a look at the speed of sound and how it changes based on temperature, on medium, and also a little bit more look at open and closed tubes. So let's start with speed. Like all waves, the speed of sound depends on what it's moving through. We saw when we dealt with strings, we could make the wave move faster by increasing the tension in the string. And essentially that's because we increased the restoring force. By putting more tension in the string, we were forcing the string to want to return to its position, its rest position faster. Well, the same is true for a longitudinal wave, a sound wave moving through any kind of matter. If the force that wants to restore the particles to their original position is stronger, then the wave is going to move faster. And we know solids have the greatest attraction between particles. That's why solids are solids. Those particles are locked in position by very strong forces of attraction, which means solids are going to be the fastest conductors of sound. Gases are going to be the slowest because in a gas the particles are way spread apart, the forces of attraction are fairly weak. So a particle that's going to transmit sound has to move quite a distance, hit that thing, and then bounce back, and so that wave propagates slower. However, we can still manipulate the speed of sound in a gas, right? This is all dependent on how fast these particles can smash into each other and bounce back. Well, if we speed up those particles, then they're going to move around faster and sound is going to move faster. And the way we speed up particles of air or any kind of matter is to heat them up, which means the speed of sound in air is temperature dependent. And we actually have a quick little equation that gives us a pretty good estimate of the speed of sound in normal temperatures, somewhere between, minus 10 degrees Celsius and 50 degrees Celsius. This equation ought to give us a fairly good result. So what we have is 331 plus 0.6 T, where T is the temperature in degrees Celsius. That gives us the speed of sound. And the common one we use, 343, that's for the speed of sound at 20 degrees, right? 20 times 6 is 12, or 0.6 is 12. 12 plus 331 is 343. So at 20 degrees Celsius, sound moves through air at 343 meters per second. It moves through liquids faster and solids even faster than that. Now let's take a little bit of a look at these open and closed tubes and effective length. So what we have with an open tube, remember, is open, we're referring to boundary conditions, and an open tube is open on both ends. So the top and bottom in this particular tube are open. It's an open tube. And since the boundary conditions are the same, that means the ends of the tube have to match. That means they're either both antinodes or both nodes. And what that means is our fundamental wavelength, our first wavelength, if you will, is equal to twice the length of the tube. Now, we can use this together with the speed equation, or the wave equation, to figure out the fundamental frequency, where we can say the fundamental frequency is equal to the speed of sound, v, divided by the wavelength, which in this case is 2L. And we can extend that a little bit farther to the nth frequency, or the nth wave, right? Because if we're dealing with the wavelength of the nth harmonic, then what we actually have is 2 over n times L, and that means our frequency, our nth frequency, is given by n times V over 2L. Now, we could also say that the nth frequency is n times F1. This is true for all integer values of n, n1, n2, n3, n4, because our fundamental frequency, our fundamental wavelength, is a half of a wavelength, and we get overtones every half wavelength. So every half wave step starting on half a wave. The same is not true for a closed tube. A closed tube has one end open and one end closed, which means we have opposite boundary conditions, which means one end is a node and one end is an antinode. So we have opposite boundary conditions in here, which means the shortest wave, longest wave, fundamental wave, that'll fit there is actually equal to 4 times the length of the tube. And the nth wave, the nth harmonic wavelength, is given by 4 over n times the length of the tube. However, we've got to be careful with this because our fundamental is a quarter wave, but the next wave that fits in there is on half a wavelength again, right? We've got to get from an antinode to an antinode, which means we've got to take a step of a half a wavelength, but our fundamental was a quarter wavelength, which means we're taking it in steps, 2 steps of quarter waves to get a half wavelength, which means we're not taking every step of the quarter wave, we're taking every other. So we don't get every frequency. So like before, we're going to have a frequency equal to the speed of sound divided by the wavelength, 4L for this one. Or, right, the nth one, Fn, is given by n times V over 4L. But the problem is we don't get every n. We only get n of 1, 3, 5, the odds forever. So, and then of course same equation, F1 equals n times F1. Sorry, Fn equals n times F1. So similar equations for this. However, we only get odd harmonics on closed tubes because we only get every other quarter wave. We get all of the harmonics on open tubes because we get every half wave. The other thing that we have to pay attention to is the length of the tube versus the effective length of the tube. The effective length of a tube is a little bit longer than the length of a tube because the antinode occurs just outside the end. And how far outside depends on the diameter of the tube. So this equation that we have, the d is the diameter of the tube. So for a narrow tube, it doesn't make much of a difference. For a bigger tube with a bigger diameter, it can actually have quite an effect. And you guys saw this in lab. Our results didn't quite match up, and they matched considerably better when we took into account that, oh, the effective length of the tube is a little bit longer because that antinode occurs outside. Now we have to add on 0.33d for each open end. So if we have a closed tube, we add on the length of the tube plus 0.33d. If we have an open tube, then we've got to add that on twice, once for each end. So the effective length, if you will, L effective, is given by L plus 0.66d.